Okay, thank you for the introduction. I'm Jinkun from New York University. Today I'm happy to be here to present our work. So this is joint work with Lingfan Yu and Jinyang Li. So we know that large language models have incredible capabilities, but they are actually very costly to serve. Um, for example, DeepSeek has reported that they cost around $87,000 daily to serve their model. And there was also a report about ChatGPT that estimated around $700,000 of computational resource cost daily. So it is important to reduce their costs and in order to make them more widely applicable in practice. So in this work, we focus on we focus on a very similar setup as the previous work, Sketch Cache, which is also this multi-turn conversation, where the user sends one request to start one conversation turn. And in this kind of workload, the user request will be prepended with chat history in every turn. So in this example, you will have this concatenated input for the second turn here. So we found that existing systems back in 2023 when we started this project were stateless. As a result, they couldn't work well under this scenario. So specifically, they when process one user request, they will generate a state for every, also known as a KV cache, for every token, and the KV cache up to the first output token is generated by the prefill phase, and the remaining token states are generated by the decoding phase. But because they are stateless, they will drop this KV cache after serving the request, and in the next turn, they will, during this prefill phase, they will need to recompute this discarded state, which results in a lot of computational resource waste. Therefore, rather than discarding a cache immediately in Pensieve, we instead try to cache the KV cache, the state, across turns. But one immediate problem is we have very limited GPU memory. For example, we may only have 40 gigabytes of memory, as you have also seen in the previous presentation from Hcache. And it can only hold a very small amount of tokens, very small number of conversations. So instead of using storage as the previous talk, we use CPU memory here. And we offload when GPU memory is full, and we retrieve when we need to do the prefill in the next turn. CPU memory is also not very large, 5 to 10x only. Also, when CPU is also full, we drop tokens out of the system and recompute as needed. So there are two main technical challenges here. The first is on the eviction path, basically what tokens to offload from GPU to CPU or to drop from CPU to out of system. And the second challenge is on the retrieval path, basically how to repopulate the KV cache to GPU efficiently. So Pensieve's solution to the first challenge is a new eviction policy. Our insight here is that tokens at the beginning of the chat history are cheaper to recompute than those at the end because of the causal attention mechanism, which says that computing one token state only depends on all the tokens in front of it. So in this 4 token example, processing T2 only requires the KV cache or the state of the T1 and T2 token, while T4 needs all the 4 tokens, doubling the cost. Therefore, more precisely, we will have this relationship, this linear relationship between the cost of computing the attention of one token versus its position in the chat history or in the context. Notice the log scale on the x-axis. So our eviction policy then adopts the 2 preferences. The first one is to evict tokens from the beginning, And next is to evict the longest inactive conversations. And then we use a score to balance these two preferences, which is simply dividing the cost of recomputation by the time since the conversation this token belongs to was last active. You may have been aware of many concurrent works. They also do this kind of prompt caching similar to us. So let me highlight the difference here. They evict from the end of the context while we evict from the beginning of the context. So this is a crucial difference because for longer context, the tokens in the front is cheaper to compute. So the longer the context, the larger the cost difference will be. However, this unique eviction policy also creates new challenges to our retrieval path. Basically, now our KV cache memory can be a bit complicated. So initially, when we don't do any eviction, everything is in GPU. But as GPU becomes full, we evict tokens to CPU. But as CPU also becomes full, we drop tokens out of system. This creates this complicated layout where we have hosts at the beginning. We have tokens residing in different devices. And even for those tokens are in the GPU memory, they are not necessarily contiguous in memory because of a similar reason as the paged attention. So to complete this pre-fill phase, what we need to do is 3 steps. Recomputing the drop token retrieved for the CPU tokens, then pre-fill for the new request tokens. If we separately compute the 3 steps, we are not able to saturate the GPU's compute or memory resources. So we need a more efficient way to streamline these 3 steps. Here our solution are a customized multi-token attention kernel with overlapped KV cache retrieval. We call that each token's KV cache spans across multiple layers evenly, and when we evict a token, we will evict the KV cache from all the layers equally. So this makes the KV cache layout for all the layers are the same as each other. Then for the tokens in CPU, to retrieve them back to GPU, we used a separate copy stream to retrieve them layer by layer so that we can overlap it with the computation. And for these 2 holes in the KV cache, what we do is we use a customized kernel to compute both at the same time in one kernel launch. And between these 2 streams, we insert CUDA events to preserve the data dependency. So how do we design this multi-token attention kernel? Let's revisit the standard attention computation pattern first. This attention essentially is computing a matrix multiplication between the query and key matrices. After that, you apply an attention mask, which is a 0-1 valued mask on the computed result. What we found is, in our case, these rows corresponding to the tokens cached in GPU already have their results available in the cache. So why not just use the results from the cache? Yeah, and then we can only recompute for the remaining rows. But so this results in this ragged attention pattern. However, this new pattern is actually not able to be directly computed with existing pre-filled kernels, not a paged attention kernel. The reason is paged attention is designed for decoding that produces 1 token at a time, while in our case, we need to pre-fill multiple tokens at a time. For flash attention and similar pre-filled kernels back in 2023, they were not able to support this RAG attention. They also couldn't support the discontiguous KV cache. So we decided to build our own kernel. We extended PyTorch's attention kernel to support the paged KV cache. And for the rag attention, we separate this matrix modification into two smaller metal modes. And then each of them has a more regular mask, and they can be supported by the PyTorch kernel. Oh, by the way, we also, although we separate them and treat them as two different requests, as shown here, but we still batch them in the same, we process them in the same kernel launch. Yeah, so these two masks, because they are supported by the original kernel design, we can reuse most of it when developing our new kernel. So there are more optimizations, like how we unify the prefill and generation, how we do multi-GPU, and etc. Please refer to our paper for details. So for the evaluation, our first experiment uses a single GPU setup with a workload generated using shared GPT dataset to sample the user prompts and Poisson distribution to generate a user request arrival time, and the exponential distribution to simulate this sync time, which is the time from when the user sees the model response to when the user sends out the next request. The baseline is an earlier version of VLLM that doesn't cache states across turns, basically the stateless version. And we show the 90 percentile request latency versus the throughput graph, where the latency is normalized by the number of output tokens. And compared to VLLM, which is the blue curve, we achieved 33% more throughput. And compared to the yellow curve, which is a version of Pensieve that does not use CPU, but only GPU as the cache, we see we achieved a similar improvement, which demonstrates the importance of using both CPU and GPU memory as the cache. The next experiment is on a larger model with multiple GPUs. Here, the size of each token state increases by 2.88x, but because we use for GPUs, our memory capacity increases by 4x. So effectively, we have more cache space per token. As a result, compared to the baseline, we achieved more improvement over this single GPU setup. And the next experiment is on group query attention, which is a technique that reduces the size of KB cache by a factor of the number of KB heads, which is 8 here. So in this case, we achieve an even bigger improvement than the previous setups. It shows that Pensieve is more effective when per token KB cache size decreases, which is a general trend we see today. So yeah, since this is a very fast-moving area, I would also like to compare to some of the concurrent works to better present the difference here. So there are, so I think the first line of work tries to offload to local disks or remote storage for this caching. This includes cached attention, cache gen, and DeepSeek. Compared to these works, their approaches are orthogonal and can be integrated with Pensieve to further improve performance. And the second line of work tries to explore this reuse opportunity across different conversations, including prompt cache and SGLang. They target these kind of applications where different conversations are likely to share common prefix. So it makes sense for them to, evict from the trailing and preserve the prefix. While for us, we evict tokens from the linear because we are targeting this chatbot scenario where different users are unlikely to share exactly the same chat history. Yeah, so in summary, we identified a problem where existing serving systems are stateless. As a result, history is recomputed. And to address this problem, we cache history state across turns, propose a normal eviction policy and an efficient kernel implementation. And with that, thank you for your attention, and I am happy to take questions.